Okay.
Ready to go?
I'm ready.
Okay. On Monday, May 16, Ken is giving a keynote presentation at a scientific meeting. The presentation is titled UIC Single Pulse Shock, Tube Studies of Fuels, and the unanswered questions they raise. Today he will give the first 5 to 7 minutes of the talk. Now here's Ken.
Can you see it?
Yes.
One more. Have you ever started a scientific study attempting to answer some well-posed scientific questions, and then have found in the course of doing that study, more questions were brought up, and in many cases, unanswerable questions, but perhaps questions that led to new proposals and maybe new research. Today, you're going to hear about UIC shock tube studies that have done exactly that. In the course of studying a variety of fuels, questions were raised that have led to unanswered questions that you might find thought-provoking and perhaps the kind of questions that would encourage you to pursue new research directions. Before you hear about those studies, a review of the UIC shock tube would be appropriate. Everything's backwards. So the UIC shock tube, shown here on the top schematically, has a high-pressure driver section filled with helium gas, separated from a lower-pressure argon-filled section, which contains a hydrocarbon, a fuel of interest, separated by a diaphragm, piece of metal, that's pre-scored so that it will break at certain pressures. When that diaphragm breaks, a shock propagates down the tube. A shock is a discontinuity in the flow pattern behind which pressure and temperature is raised. And that shock travels down the tube, as you can see here, hits the end wall and bounces back. When it bounces back, it creates a high pressure, very high pressure, high temperature region, shown in red here, where chemical reactions take place. Chemical reactions of the fuel, the hydrocarbon fuel. On the breaking of that diaphragm, there's also an expansion wave, a rarefaction, which itself bounces off the other end wall, comes back down the tube, and after about 2, 3 to 4 milliseconds, drops the pressure in that red region, ends the chemical reactions, ending the scientific view time. The actual shock tube is shown here. You can see the driver section at this end, the diaphragm section here, the driven section there. It's wrapped in yellow insulation because the shock tube is heated in order to work with condensable large molecular weight fuels. And the operating condition of this high pressure shock tube is from about 800 to 2500 degrees Kelvin. The pressure can go from 15 bar to 1000 bar. Yes, we run this at 1000 bar, very, very high pressure. You're scientists. You know what I'm talking. You wish. Okay, and the reaction times typically are from 1 to 4 milliseconds, although by tailoring the driver gas appropriately and doing certain other modifications, it can be extended 6, 8, even 10 milliseconds. And the tube is heated to 100 degrees centigrade. At the very end of the tube, you can see here, there are heated lines that take gas samples from out of the shock tube after the reaction is complete, so that gas chromatography can be used to analyze what's in the tube after the reaction. And what's in the tube are the products of the chemical reaction that occurred when that temperature and pressure was very hot. And that's what the studies are about, finding out what those chemical species are after the fuel has reacted at high temperature and high pressure. There is another shock tube in the laboratory that complements the first one, a lower pressure shock tube, seen on the left here. Its pressure range is from 0.1 bar, subatmospheric, to 10 bars, and it almost overlaps the high pressure shock tube operating conditions. The two tubes together are complementary in range and give a very wide dynamic range. For those of you, I don't expect anyone here, for those of you who know John Kiefer, when he was active, this was his tube, which I got when he retired. The shock tube, as was mentioned, produces a shock wave that raises the pressure up, and during that high pressure region creates a high temperature, and then the rarefaction wave comes and drops the pressure. You can see that here from a real pressure trace, where the pressure jumps up, stays high in this plateau, and then drops down exponentially. It's during this high pressure region where the reaction takes place, and after the rarefaction occurs and stops the reaction, that samples are withdrawn. So this tube is perfect for measuring chemical species as a function, the way it's done, of different temperatures at a fixed pressure. And as you will be seeing now, typical results plot species with respect to temperature at fixed pressure and time, and those are the kind of shock tube data that have led to a number of unanswered questions that you may find provoke further ideas of research on your part. I suggest you come back next week for the rest of this presentation, which is only 1 hour long. Thank you, Tim.
That's quite a key tease, Ken, I'm sure.
I'm sure people will be back.
Absolutely chomping at the bit to come back here and hear the rest of this riveting speech you have here. All right, now Walter is going to be doing a baccalaureate speech. He's requested that we have